So today we're going to look at summary of curve sketching. All right. And for you to sketch a curve, there's certain things that you need to follow. So there's certain things I'm going to ask you. Curve sketching is obviously one of those stuff that you know that will always ask you to sketch a curve. And now it's for you to understand what are the steps, all right, the procedure. So let's go straight into it. So let's look at the guideline. Let's start with domain, all right? So the domain of a function depends on what the function is, all right? You can see here I say if you have 1 over some function, therefore, because that function appears at the denominator, you can say that the function is at the denominator, you're going to say that that function cannot be equal to 0. For example, if I actually was a domain of 1 over x plus 1, for example, you're going to tell me that x plus 1 cannot be equal to 0. So I'm just going to write it so that everyone can see. So I'm asking you for the domain of something like this, 1 plus x. All right. So obviously you're going to say this bottom piece here cannot be equal to 0. Hence your x there cannot be equal to minus 1. It's as easy as that. All right. Now let's look at another scenario. What happens if the function is under a root? So you have square root of some function. All right. Everything inside that root has to be greater than equals to 0. All right, that's how it works. And now, if the root appears at the denominator, you need to say that everything under the root needs to be greater than 0, because you can't say greater or equal to at this point because it appears at the denominator. All right. And then another function you're going to see sometimes is logarithmic function, so ln or log function. Obviously, for ln function, you see everything that goes inside the lane has to be strictly greater than 0. That's how it works. All right. There we look at intercept. So all of that is just to see where, for what x value is a function defined. We look at intercept. Intercept is where the curve is going to cut your coordinate axis. All right. So for the y-axis or the intercept, you just set x to be 0. So if this is my xy plane, and I have a curve that does that, you see that when it cuts, x equals to 0 is where it cuts the y-axis, right? And then y equals to 0 is where it cuts the x-axis. So that's basically how it works. And that gives you the intercept. All right. Another important aspect is symmetry. Symmetry, we want to know if a function is odd, is even, or is some sort of periodic function. All right. So for an even function, we say that f of minus x, we check to see what happens when I replace x with minus x. And if I get exactly the same function, then my function is an even function, all right? And if the function is odd, then f of minus x is just going to be minus f of x, all right? And then take note that your trig functions are periodic function. So I would restrict you, so sine and cos, they had the periodic, and the period is 2 pi, while for tan, the period is pi. So what that means is from 0 to 2 pi, once you move after 2 pi, the function starts again, all right? It repeats itself. That's why if I give you a trig function, I will usually restrict you on what the domain is, all right? Now that we understand symmetry, let's move to the other properties. At every stage, you need to let me know if there's something that you don't understand. All right. So you can raise up your hand or you can stop me, but make sure that you ask your question. You have to understand what is happening. Now let's look at asymptote. All right. For asymptote, a function can have either vertical or horizontal or both of them. All right. We'll even see a special scenario where some functions have something called slant asymptote, but we're going to get to that. For now, let's discuss horizontal and vertical. For horizontal asymptote, the way it works is you just a limit as x tends to plus or minus infinity of your function. It will give you some value L, all right? And then you say y equals to L is your horizontal asymptote. For some functions, when you take the limit as x approaches infinity, you're going to get a different result compared to when you take the limit as x approaches minus infinity, all right? But if your function is an even function, all right, meaning that f of minus x equals to f of x, it means that the limit as x approaches plus or minus infinity will more or less give you the same result for most cases, all right? Now they say remember the roots. So there are special functions, especially when roots are involved, all right? Once you see a root appearing in your function, it means that you need to test the limit as x approaches infinity and the limit as x approaches minus infinity separately, all right? Because there's a high tendency that you're going to get different results, all right? I'm going to explain something quickly. If I give you something like, let's say, square root of x squared, all right? Now, most of you are quick to tell me that this is equals to x, all right? Well, it's not necessarily true that it's just equals to x. It depends on what x is. By definition, the square root of x squared is the same as the absolute value of x, all right? So absolute value of x, you can't just say it's equals to x. You see that it depends on if x is positive or negative. So in this case, when the limit as x approaches infinity, in this case, square root of x squared is just going to be x, all right? Because you can see that x is approaching infinity, and infinity is towards the positive spectrum, all right? But now, the limit as x approaches negative infinity. You see that negative infinity, you're heading towards a negative spectrum or the negative side of your number line. Therefore, this absolute value becomes minus x actually, all right? It's not going to be x. It's going to be minus x. So why am I mentioning this? It's because most of you tend to ignore this critical aspects. All right. Once you see a root, like I said, test x approaching infinity and negative infinity separately, always. All right. For most other functions, if you take the limit as x approaching plus or minus infinity, it gives you exactly the same result. So you don't have to do them separately. All right, but you get used to when we do a lot of examples, and if you do my homework problem, you're going to be able to identify those functions where you don't have to test um, the limit as x approaches infinity and the limit as x approaches minus infinity separately. That was horizontal asymptote. Now let's look at vertical asymptote. All right, vertical asymptote, the key is your domain. If your domain in step 1 is wrong, I can tell you that so many things are going to go wrong. All right, your domain, I can tell you now, is one of the most is the most important step. All right, in this whole thing. If you get it wrong, your sketch will be wrong, your asymptotes will be wrong. In fact, everything is going to be wrong. It's as easy as that. All right. So once I'm marking your script, and the first step, which is domain, you get it wrong, I already know what is going to happen. In most cases, you just get a method mark for knowing maybe the steps of how to sketch a curve. But if you need to always pay attention when you do the first step of curve sketching, which is the domain. Make sure you get it correct, like I said, because if you get it wrong, it's game over. All right, you're going to lose so much marks, and I can tell you already that curve sketching counts the most marks. All right, I'm sure you've seen them in previous tests that you've done. Usually counts for a lot of marks, so you don't want to lose marks. And how it works is, on your domain, you have some restriction. They say x cannot be equals to a. All right, for example. That restriction is what you're going to use when you're looking for vertical asymptote. So if x cannot be equals to a, it means that something happens when I approach a from the right or the left. All right. So what I'm going to do is I take the limit as x approaches a from the right. I just test the sign to see if I get plus or minus infinity. All right. How does it work? For example, let's say a is 1, and you testing the limit as x approaches 1 from the right. Obviously, it means you have to test values like 1.1, a value close to 1 from the right. You can use 1.1 or 1.05 even. Plug it into your function and just look at the sign. If the output you get is positive, then you know that it approaches infinity. If the output is negative, you know it's minus infinity. All right. And then you do the same thing for the limit as x approaches a from the left. You see if it's going to give you positive or negative infinity. Then your conclusion is that x equals to a is a vertical asymptote. All right. So vertical asymptote is x equals to something. All right. Horizontal asymptote y equals to something. I've seen many times people tend to swap them around. they're doing vertical asymptote, but they're showing me the computation for horizontal asymptote. So don't swap them around. If you do that, it means you don't know what to do. You simply get 0. All right, it's as easy as that. It's a 0. Increasing, decreasing. We did that in our last class. So increasing, decreasing, you know your first step, you need to find first derivative. You get your critical values. We say for those critical values for which your first derivative is greater than 0, that interval we call it increasing. And when the first derivative is less than 0, we call that decreasing. All right, those are basic steps. All right, let's keep going. We look at local max and local mean. Local max and local mean now is when you have a change of sign. So from increasing, you can see here, I have increasing and I have decreasing. You see, I have that pattern, that shape like that, all right? It tells me that there's a turning point, there's a local max at that critical value, all right? And if I have decreasing followed by an increasing, then I have that kind of shape. Another, there's a turning point, which is a local minimum at that critical value. It's as easy as that. And then concavity, once you hear what is the concavity of the function, the first thing that comes to mind is second derivative. You must differentiate the function for the second time, all right? Some people tend to use the result from the first derivative to try and compute concavity. No, you're going to get a 0. First thing I need to see is that you do the second derivative. And you do the second derivative, you get some critical points, you put it on the number line, you test. If you get positive, it means it's concave up, and if you get negative, it means you have concave down. All right, we're going to do example. I'm going to show you how it works. And then there's something called inflection point. Inflection point is when you have a change of concavity. All right, so if you move from concave up to concave down, then it means that at that number or that critical point or critical number, there is an inflection point. All right, and if you move from concave down to concave up, against an inflection point. But very important, we say that an inflection point or an inflection point, yeah, it occurs at some number x equals to c, provided that c has to be in the domain of the original function. All right. So when you compute the inflection point, you should be able to plug in that x value into your function and get a valid output. All right. If you have a change shift concavity, but at that x value, the function is not defined at that x value, we don't call that inflection point. All right. So that's a little trap. You must watch out for that. So you always test to see that at the inflection point, the function is defined at that x value. Very, very important. All right. And obviously, you just need to go ahead and sketch. All right. You see the 9 steps. After the 8th step, the 9th step is just to sketch. So to make life easy for you, I would give you the recipes. I would say, give the domain, give me increasing, decreasing, and so on. I might exclude some of these steps since I don't want to give 20 marks for one tiny question. But I might ask any of these 8 steps, and obviously, you sketching is something that's a must. You must know how to sketch. All right. Now let's look at example 1. Let's go step by step and let's go slowly so that everyone is happy. This is sketch the graph y equals to 2x squared over x squared minus 1. All right. The first thing you need to think, what kind of function is a rational function? I see a polynomial of a polynomial. All right. Okay, no problem. Let's now that I've identified a rational function, it means that for the domain, the bottom piece cannot be equal to 0. You see, identifying the function is very important because it helps you to answer the most important question, which is the first question. What is the domain? Like I told you, if you get it wrong, you're going to lose at least 70% of the marks. All right. So x is an element of real number, and x cannot be equals to plus or minus 1. Because we simply just equate this bottom piece and say this bottom piece cannot be equal to 0. All right. Let's move to 2. 2 is step 2 was to find the intercept. Look at this function closely. If you set x to 0, you just get y 0. And if you make y equals to 0, you cross multiply, you just get x as well to be equal to 0. So you see that the origin, so your curve passes through the origin. All right, that's basically what it means. And then let's look at symmetry. Symmetry, you see you plug in f of minus x. It means everywhere you see x in your function, replace it with minus x. Notice it, you get exactly the same function. All right, f of minus x is equals to f of x. Therefore, it's an even function. All right, and what does it mean for something to be even? All right, it means that if you have one piece appearing on this side, you can reflect it about this axis, and the other piece is going to appear there. All right, so it's nice to know symmetry so that you can sketch one piece of the curve and then just reflect it. All right, and get the other piece. Now let's look at horizontal asymptote. Horizontal asymptote, we say that you just take the limit as x approaching plus or minus infinity. Notice in this case, whether it's positive or negative infinity, you get exactly the same result of 2. Therefore, the conclusion is that y equals to 2. Guys, not x equals to 2. It's y equals to 2 is a horizontal asymptote. All right. Vertical asymptote, like I said, vertical asymptote works hand in hand with your domain. You look at your domain. You ask yourself, what was the restriction I saw at the domain? X cannot be 1 or minus 1. So it means for vertical asymptote, I need to test and see what happens to my curve when I approach those restrictions, which is 1 and minus 1. So as x approaches 1 from the right, what happens? You get infinity. When it approaches 1 from the left, you get minus infinity. Remember, this infinity and minus infinity, like I said, you just testing the sign. I don't want you guys to give me numbers. All right, just tell me if it's infinity or not. Well, what I mean is, for example, if I say the limit as x approaches 1 from the right, it means test with a value like 1.1. Look at the top here, 1.1. If I put it in here, obviously where you square it is going to be positive. Look at the bottom, 1.1 squared minus 1. Obviously something bigger than 1. So positive over positive is positive. That is why I end up with positive infinity. However, if you test from the left, at the bottom here, you're going to get negative result. All right, some value that is less than 1. If you square it and you subtract 1, it's still going to be negative. All right, and then you also do the same thing for minus 1. Limit as x approaches minus 1 from the right, and from the left, tell me if it's positive or negative. Then this is the most important conclusion. You need to say, therefore, x equals to plus or minus 1, they are vertical asymptotes. All right, because if you just give me this limit and they don't tell me that therefore x equals to plus or minus 1 vertical asymptote, it means that I'm going to write in your paper, okay, what does this limit mean? The limit that you've computed, what does it actually mean? What you are trying to do here, this value is telling me infinity and minus infinity, you're trying to conclude that x equals to 1 and x equals to minus 1, they're vertical asymptote. All right. Now let's discuss increasing, decreasing. Increasing, decreasing, like I said, the first step is your first derivative. You find your first derivative, simplify as much as possible. So simplify up to a nice form where you get some rational function, some polynomial over some polynomial. If you're dealing with root function, simplify to a point where there's nothing that's common, nothing that you can factor out or that can cancel from the top and the bottom. All right, so simplify as much as you can. The next thing is you find critical points. All right, how do you get critical values? You ask yourself, when is the first derivative equals to 0? Is a rational function is equals to 0 when the top function is equals to 0. So you just say minus 4x equals to 0. That's why we have x equals to 0 to be a critical value. And then you say, where is the first derivative undefined? Clearly, you can see that this bottom piece here is undefined when this bottom piece equals to 0. So just equate x squared minus 1 all squared equals to 0. What do you get? You get plus or minus 1. So you have 3 critical numbers there, which is 0, 1, and minus 1. Like I said, put it on a number line and then test the sign. So choose a value slightly less than minus 1. You see here I choose minus 2. You see I test, I get positive. Positive means increasing. All right. Between minus 1 and 0, you can use minus half. Again, it says increasing. And then between 0 and 1 is decreasing because it's negative. And then between 1 and all the way to infinity, I choose 2 and it's decreasing. All right. So, and this statement that I wrote here is, where are you testing? This is how some people get this specific section wrong. People get this section wrong because they don't even know where to plug in these critical values. You plug the critical values, look at what I'm showing you there. in your first derivative, not your original function. All right, please remember that. When you do increasing, decreasing, and you plugging in or you're testing the sign, you use the first derivative function that you have. All right, so your first derivative function helps you to get the critical values, and there's also the same first derivative function that you're going to use to test the interval of increasing and decreasing, not the original function. All right. And then how do you if you draw a number line, you show me arrows, automatically I can see directly from there that you know what you're doing. You have marks for doing that, but you can't get full marks. You need to show me that you're able to interpret what that number line means. Increasing, you know, is x element of minus from infinity to -1, and union from -1 to 0, and then decreasing from 0 to 1, and then union from 1 to infinity. All right, guys, be careful. This is supposed to be minus infinity, not infinity there. Let's just go back so that I show you why it's minus infinity. All right, so if we're talking about increasing, notice it increases for every value less than -1 here. So for minus infinity all the way to 1. Now be careful. This is a nice example because some people will be tempted to see that, wait, it's increasing this interval, it's increasing this interval. Why don't I just say it's increasing from minus infinity all the way to 0? The reason why you can't say that is because the function itself is not defined at -1. Why? -1 is part of the restriction that you had in your domain. Remember, the domain of the function is such that x cannot be 1 or -1. So you can't give me an interval for increasing and decreasing and you including those restrictions that you had in your domain. All right, doesn't make sense. All right. So now that you're happy, let's move on. And then we talk of local max and local min. Remember, local max, local min. Here you see that it happens at 0. Let's go back and see if that is true. You see that at the critical value of 0, there's a change of sign. So you have increasing on the left, and then you have decreasing on the right. All right. This, I told you already, this tells you that there is some sort of turning point there at x equals to 0. So at x equals to 0, you have a local max. Look at -1. There's no local max or local min there because it's increasing on the right and on the left. And if you look at 1, there's no local max or local min because it's decreasing on both sides. All right, there have to be a change of sign for you to have a local max or local min. All right, and this is how you're going to solve it. You're going to say f of 0, first thing, I'll give you a mark for showing me that you know that there's a local max at the point x equals to 0. And when I put 0 into my function, remember now I'm plugging in this value into my original function. So I'll explain this again so that people don't get confused. Increasing, decreasing, you use your first derivative function. To test for local max or local min or inflection point, you use your original function. All right. Please don't confuse those. If you test local max and local min using your first derivative function, you're going to get a completely wrong answer. All right. So f of 0 is 0, and we say it's a local max. This arrow is just to show you that there was a change of sign from increasing to decreasing. All right. And concavity is second derivative. I'm going to advise you, some of you, there's nothing wrong if you just take your first derivative function and you differentiate it again, all right? And then you try to work from there. Usually, you guys make a mistake in your first derivative function, and then when you take that wrong first derivative, you differentiate it again. Obviously, the derivative of a wrong derivative will give you a wrong derivative. It's as easy as that, right? So my advice is when you're doing concavity on the side, start by doing your first check. So go back and check your first derivative. Because if you made a mistake earlier and then you carry on with the wrong result, then your concavity or your second derivative is also going to be wrong. And then everything else, your interval concavity will be wrong, inflection points will be wrong, and so on. And you don't want to lose all those marks. So please, before you do second derivative, go do it on a rough sheet. Take a piece of paper, try again, do the first derivative again, make sure that you can get exactly the same result that you had earlier, all right, before doing the second derivative. Once you're confident of your second derivative, like I said, factor and simplify as much as possible. and then find critical value. So ask yourself, when is the first derivative equals to, or when is the second derivative equals to 0, and when is the second derivative undefined, as usual. That's how we get our critical point. And notice in this case, it cannot be equals to 0 because this top piece here is an irreducible quadratic function, all right? Meaning that if you equate 4x squared plus 1 to be equals to 0, it's just undefined. There's no way on earth that 4x squared plus 1 can be equals to 0. So we know our second derivative cannot be equals to 0, but we don't stop there. We test when also is the second derivative undefined. That happens when the bottom piece is equals to 0. I know it's going to be undefined. So I say x squared minus 1 cubed equals to 0. X gives me plus or minus 1. There we go. You see? You end up with plus or minus 1. All right. And then test again. So test some value less than minus 1. You see, I choose minus 2. And if you get a positive result, it means it's concave upward. And then choose between minus 1 and 1, you can use 0. If you get a negative result, you know that it's going to be concave down. Choose a value bigger than 1. Again, it's positive. That's why we have concave up. All right. And then here again, I'm reminding you where you're substituting. You're substituting those values that you had in your second derivative. All right. So this minus 2, 0, and 2, so these values on top here that I'm choosing, which are those values within the interval that I'm testing using second derivative. I've seen some students at concavity, they're using their first derivative function. Some even use the original function. And then they ask me, say, but I did the right thing. Why do I have 1 out of 8 or 1 out of 10? All right. So please make sure you check your work. How do you read interval concavity? We see it's concave up from minus infinity all the way to minus 1. You use union because there's two intervals you're working with, and from 1 all the way to infinity. And there's concave down, you can see from minus 1 to 1. Notice I'm always using these round brackets, right? I'm not including this endpoint because the function itself is not defined at those endpoints. Very important. So whenever you give me interval of increasing, decreasing, or concavity, use round brackets, always, all right? Don't try to include because it's an observation that we're trying to make. We want to see the behavior of the function when I approach an asymptote. You understand? So you can't be trying to include the endpoints as well. And once you have concavity, you almost there. You're getting close to being ready to sketch. You know already the next step. With concavity comes what? Inflection point. But before I show you what the solution is, you can see for yourself that there's a change of concavity from concave up here to concave down here. All right. And at 1, there's a change of concavity on the left from concave down to concave up. But what is the second question you need to ask yourself? Does it mean that there is an inflection point at 1 and minus 1? The answer is not necessarily true because I need to test if x equals to 1 and x equals to minus 1, they're part of the domain of the original function. In this case, they are not. Therefore, what's the conclusion? The conclusion is that although there is a change in concavity on both sides of 1 and minus 1, there's actually no inflection point. All right, there are no inflection point. So please don't get confused. There are no inflection point. Now to sketch, if you remember well, I told you that symmetry is going to help you a lot is to sketch your graph. To sketch your graph, the first thing you need to do, obviously, is to draw a nice XY plane and label them. Don't assume that I know what is X and what is Y. Label everything, all right? Show me what is X, what is Y. I've seen before a student, not actually one student, do this. They call this one X, and then they call this one Y. They're not wrong. They're just using a different point of reference. But now when I'm reading this or when I'm interpreting the sketch, I'm going to interpret it based on what I'm seeing, all right? So I'm going to use this scale that you give me. So the worst case scenario is someone who doesn't even tell me which axis is X and which one is Y. I may assume that this is what you're trying to sketch, all right? Whereas maybe this is the actual sketch that you're trying to do. So label your axis. Secondly, label asymptotes. Asymptotes, vertical, horizontal. So your axis, XY axis, and then show me your asymptote. We use dotted lines, all right? We use broken line. Y equals to 2 was horizontal asymptote. You use broken lines that passes at 2, all right? And then we have vertical asymptote at minus 1 and 1. You see again, I have the broken line. All right. There you go. If you can do this, every step you do counts for mark. Now you ask yourself, how is the concavity? We know that there is a concave up. There's a concave up from 1 to infinity. There's a concave up from minus infinity to minus 1. And there's a concave down from minus 1 to 1. All right. So look at your concavity. But before you do concavity, another important thing is you want to see, you want to generate a picture in mind where the curve actually cuts your coordinate axis, which is something called the intercept. Very important. So after you put your vertical asymptote, horizontal asymptote, use a pencil or something to mark all the intercept. You want to see where the curve is going to pass. All right. So the first intercept we saw there is that, or the only intercept we have in this case is the origin. My curve passes through the origin. All right. So now I have a good idea. I need concave down, and it has to pass through the origin. Obviously, there's no way that I'm going to draw something that goes up and does this. It's impossible, right? Because I said from minus 1 to 1, I need concave down. So the only possible sketch is this one, right? If you try to do anything here at the top, obviously you'll be doing a concave up instead. So if you try to do this, that's not concave down, it's concave down. So it's concave up. The green one is concave up, the red one is concave down. So your concavity helps you now to link the point. But we're not done, because we say that there's concave up from minus infinity to minus 1. Now ask yourself, can I draw it anywhere down here? The answer is no, because the behavior of a curve when it approaches an asymptote is that it gets close and close to the asymptote, but it tries not to cut it. All right. So by definition, if you remember from high school, they told you that asymptote does not necessarily cut, or your curve must not cut an asymptote. So in this case, if you have that in mind, you know that the only way I can draw this, and it has to be concave upward, is if I draw it up here. All right. So I have that kind of shape. Again, I need another concave upward here. I know very well that I can't do anything on this side, because if I try to draw anything here, for example, that doesn't look like concave up. It looks like concave down, you see. So that alone tells you that your graph has to be somewhere up there. All right. And why we needed symmetry is because one student can ignore this piece of the graph. They focus on sketching only this right-hand side, and then they just reflect it. All right. It's a reflection about the y-axis. You see that I have one piece here. If I reflect about the y-axis, this piece appears there. If I have this, something like this, let me just change the color so that you see what I'm talking about. So if I have this other piece here at the bottom, and I reflect about the y-axis, the other piece will be somewhere there. You see, that's why symmetry is very important. It can help you to sketch your graph very quickly and very accurately. All right. Any question regarding our first sketch? Ask your questions, guys. All right. So silence, I assume that everyone is happy. So you all understood that example. Let's see different kind of functions. So the first function was a rational function. Now let's look at example 2. Now we're dealing with root function. All right. As usual, what did I say? The first thing is to look at domain. And when you're dealing with root function, you need to be very careful. Root function, they're one of those complicated functions that you don't play with. All right. In this case, because the root is at the bottom, if you remember in the beginning when I explained domain, I said that if your root appears at the denominator, you see that the function under the root has to be strictly greater than 0, not greater than or equal to. Because if it says greater than or equal to, you're saying that I can divide by 0, basically. So it has to be strictly greater than 0. And if you do that, you see that x is greater than 1. Now, this interval that you have here for your domain, so x element from -1 to infinity, it's a tight restriction. It means that this is where your graph belongs. You understand? There's no piece of your graph that is going to be outside of this domain. All right. That's the reason why our first step is to find domain. Because domain tells us where our curve is going to exist in the first place. All right. I'm going to come back to domain later on. Let's look at intercept. Obviously, if x is 0, y is 0. If you make y 0, x is 0. Again, it tells us that it passes through the origin. All right. So your intersection happens on the origin. Symmetry. When I plug in f of minus x, look at what happens. At the top, minus x squared is just x squared, and then the bottom minus x plus 1. Notice that this doesn't look like our original function f of x, and it doesn't look like minus f of x. All right, it's a completely new function altogether. Therefore, it's neither odd nor even. And once you see something like neither odd nor even, it means that when sketching, you need to be careful. You can't just sketch one piece and try to reflect it. All right, you only do those reflections I talked about when there is symmetry actually. So in this case, there is no symmetry, meaning that you must sketch every piece by piece. You don't reflect stuff. All right. Let's look at horizontal asymptote. Horizontal asymptote, you say you take the limit as x approaches plus or minus infinity. In this case, what do you get? You get plus or minus infinity. Therefore, there is no horizontal asymptote. All right. I'm going to show you why. If you look at the top there, as x approaches infinity, for example, if you notice it, it just gets bigger because you square in it. All right. And when at the bottom here, for any x value within this interval that you plug in this root function, the root function is a growing curve. All right. When I use the word growing curve, it means it grows exponentially, either in the positive direction or in the negative direction. So for limit as x approaches minus infinity, it will be growing in the negative direction. In that case, you just have plus or minus infinity. And remember, plus or minus infinity is not a number. Don't just write limit and then you actually stop there. You say, oh, I'm done. All right. You're not done. Why? Because you need to tell me that this translates to there's no horizontal asymptote. So if you take your limit and it gives you plus or minus infinity or just minus infinity, you conclude that there is no horizontal asymptote. That's the meaning of that statement. All right. And then vertical asymptote, again, like I told you, your focus is the domain. So vertical asymptote, you go back to the domain. Where is that restriction? Is that restriction happens here at minus 1. They say x has to be bigger than minus 1. Clearly, it tells you that I have to test the limit as x approaches minus 1 from the right only. I'm going to explain why. All right. From the right, it gives you infinity. Therefore, you say this is vertical asymptote. The question is, why don't we test the limit as x approaches minus 1 from the left? Look at the domain. The domain says that x has to be greater than 1. It means that you can't even test values that are smaller than minus 1. Because first of all, it will not be defined. You plug in this function, you will not have any output. All right. So we don't even test the limit as x approaches minus 1 from the left, because I told you the very important thing was that domain. It tells you exactly where that curve lies. It lies between minus 1 and infinity. So you can't be testing limit as x approaches minus 1 from the left. It's not possible. All right. And then next thing, we need to look at increasing and decreasing. Obviously, as usual, you get your first derivative. You ask yourself, when is it equals to 0? You're going to get x is 0, x is minus 4 over 3. And then when is it undefined? You equate the bottom piece to be equals to 0. You get minus 1. Now, this second one has a lot of cash, all right? If you notice it here, you have some extra critical value that we're not interested in. Because I'm just going to go back. Our domain was from minus 1 all the way to infinity. And because we're dealing with the root function, it means that you cannot have a value like minus 4 over 3, which you know that is smaller than minus 1. You see? So any critical value you have, any x value that you get from here, it has to be within that domain. It has to be between minus 1 and infinity. That's why we say that we're excluding this. All right? It's not included. All right. Or you can write in another nice way. You say, but minus 4 over 3 is not an element of, you mentioned this domain here. Yeah, I'm going to give you your full marks there. It means you understand what's happening. All right. So we don't use minus 4 over 3. Our focus is going to be 0 and minus 1. All right. You see, so our focus is going to be just 0 and minus 1. Again, at minus 1, because of that domain that we had for minus 1 to infinity, You see that when I'm testing increasing, decreasing, I ignore this piece here, everything on the left-hand side of -1. Because look at the domain. The domain says that the curve doesn't exist for values less than -1. It means that there's no need to test because it will be undefined. All right. For those of you that like to test and tell me what kind of sign are you going to get. In your paper, I'm going to put a big question mark and I say how. How is that possible? All right. So if you test between -1 and 0, you get negative, means decreasing. You test for values bigger than 0 is positive, it's increasing. And again, you see, for every example we do, I tell you where you substitute it. For increasing, decreasing, you test in using your first derivative function. Very, very important. First derivative function. And then just tell me this interval. So tell me that's increasing from 0 to infinity and it's decreasing from -1 to 0. Always use this open brackets. All right. Because we just focus on the shape, the behavior of our graph. And then is there a local max or local mean? You can see at 0, there's a change of sign, right? From decreasing to increasing, it tells you that there is a local mean, all right? And how do you show me if you want full mark? If you say local mean at x equals to 0, you have 1 out of 2. If you solve it and you say that f of 0, you substitute x equals to 0 into the original function. I told you local max, local mean, and inflection point, we test using the original function. So you say f of 0, it gives you 0, and you say that is a local mean. You have the full marks because you know that at x equals to 0, there is a turning point there. And what kind of turning point? Is actually a local mean. All right. So it's this kind of shape. All right. Or we say concave upward. From first derivative, what do you do before you do your concavity? I'm sure you guys know already what you remember what I said. I said you don't just go ahead and do second derivative. You need to test again. Go back and differentiate again, simplify, and see that you get exactly the same result, just so that you don't make a mistake. All right? Because if you make a mistake, then my marking ends here in step 6. Because everything going downward is going to be wrong. It's as easy as that. If you make one little mistake, everything else becomes wrong going down. That's why you don't. The last thing you want to do is to have your domain wrong, which is step 1, because all the other steps are going to be wrong. It's as easy as that. All right. Now, if you look at second derivative, like I said, simplify as much as possible. Can this be equals to 0? Remember, to find critical points, you need to ask yourself, when is my second derivative equals to 0, and when is it undefined? Well, for it to be equals to 0, it means that the top function has to be equals to 0. All right, and that top function there, before you try to factorize this or use minus b plus or minus square root b squared over 4ac over 2a, you can do a quick test. It's called the discriminant. All right, the discriminant tells you if some quadratic function has a factor. All right, if it has root in the first place. Once you use the discriminant, this discriminant that I wrote here, like a triangle, the discriminant is b squared minus 4ac. All right, so when you use b squared minus 4ac and it gives you a positive value, it means that you have real and distinct root. If you use b squared minus 4ac, it's equals to 0, it means that you have equal root. It means you're going to get the same factors. And if b squared minus 4ac is less than 0, it's negative, it means you don't have a solution. It means don't bother trying to factorize it because it will never work. It's as easy as that. If you can manage to get a factor again, I'm going to ask you how did you do that, all right? Because it's not possible. Because this guy does not lie, the discriminant does not lie. It tells you if something has a factor, it has real roots or not, it has equal roots or not, or it has no roots at all. Then you ask yourself now, since it cannot be equal to 0, we don't stop there because obviously there has to be concavity. I can't give you a curve and then all of a sudden there's no concavity. No concavity means it's a straight line, all right? The fact that it's a curve, it means there have to be concavity. So you now ask yourself, what am I missing? Because I don't have any x value so far. You ask yourself, where is the second derivative undefined? Don't forget that extra question. Where is it undefined? You look at the bottom there, the bottom piece cannot be equals to 0. Therefore, x there cannot be equals to -1. So one of your critical points is going to happen at x equals to -1. All right, because we know that at x equals to -1, I'll have 0 here at the bottom and it makes it undefined. All right, and therefore your only critical value here is -1. What do? You chalk it on the number line. Again, look at the strange number line that I have. You see, I'm not testing anything on this side because of that domain that we had. You see, your domain haunts you from start to end. Once you get it wrong, then you're just using the wrong interval, you're sketching the wrong thing, everything is wrong. I always reference my domain. My domain was from -1 to infinity. Therefore, I don't even have to bother testing anything below -1. So I only test on this side, I get concave up. All right, so concave up is from -1 to infinity. You see, your concave up looks like your domain. All right, and again, where are we testing? We're testing using that second derivative function, not our original function. All right, to find increasing, decreasing, or to find concavity, you use the function that you differentiated. All right. Obviously, there's no inflection point. It's very obvious because you only have one interval. All right. For inflection point to happen, there must be a change of concavity. The fact that you only have one interval to work with, there's no inflection point. And then the next is to sketch. Now, did we have any horizontal asymptote? No. Do we have a vertical asymptote? Yes, at x equals to -1. So you put that broken line there to show me that this is your vertical asymptote. And then you ask yourself, there is concavity from -1 to infinity. And very important, before you even talk about concavity, is that point of intersection or the intercept. Where does your curve cut the coordinate axis? You see that it happens at the origin. And because it passes through the origin and it's a concave upward, the only possibility is the shape here. All right. Why is this the only possibility? Because look at how the graph behaves here. The graph gets close and close to my asymptote, but it doesn't cross it. All right. It means that this shape that I'm sketching is definitely 100% accurate. All right. That was it for question 2. Is there any question from your side?